This is the fourth episode of AP Stats Probability Question of the Day. Today we're working from 2012. It is a charity game where the participant pays $2 and then they spin the spinner, and this is how much the participant will get. So as the people putting on the fundraiser, we want to make sure that we're making money. So we're looking at the distribution of the net contribution to us. So if somebody pays $2 and then they spin a 0, that means that we are getting a net contribution of $2, and that happens 1, 2, 3, 4, 5, 6 out of 10 spins. Assuming this thing is fair, that would be a 3/5 chance. The probability that we get a contribution of $1 would be if they bought in for $2 and won $1, which happens 3 out of 10 times. And when our participant wins $10, that means that the net contribution was -8. We lost money on that interaction. And that happens 1 out of every 10 spins. So that is our probability distribution for the net contribution. Probability distribution means what are the values X can represent or take on, and then what are the probabilities associated to each of those values. And then normally whenever you see a probability distribution table for a discrete variable, you're going to want to calculate the expected value. So what on average will be our average donation here? What's the expected value of X? What we do is we want to take the sum over all the different X values times their probabilities. So we want to take 2 times 3/5, 1 times 3/10, and -8 times 1/10. Pretty much a weighted average of all these numbers. We take the X value times its probability, the X value times its probability, the X value times probability, and all of this adds up to 70 cents. I'm going to write units again because you really got to give your units. We want these numbers in context. So on average, you expect to get a net contribution of 70 cents. They pay $2 to play, but they win sometimes. So this is good. As the person putting on the charity, this is a good thing. We want to make $500 though. So we want to know how many times we have to play this for our average winning to exceed $500. This doesn't mean we will make more than $500. This just means that the expected value will be $500. So if we have n plays, then we want n times our expected value for one play to be over 500. So it's 70 cents for each play. There's n plays. We want that to exceed $500. So we will divide to find n. If it is a net contribution of 70 cents each time, then we want to take 500 and divide by 70 cents. And that is approximately 714 point something, 0.3. So if we want to ensure that this is greater than here, we want n to be at least 715. So we need 715 plays. Notice how I write plays as my units here. So this doesn't guarantee that we are going to make more than $500. This is just the expected value for 715 plays. So part D, we now look at this in terms of a normal distribution. So we want to know if we play 1,000 times, what's the probability that we make more than $500? And they claim that the net contribution for 1,000 plays, the net contribution for 1,000 plays has a mean of 700 and a standard deviation of 92.7, and they say that we can use a normal distribution. So I'm going to call this variable y, the net contribution for 1,000 plays. Then they claim that y is normal Y is distributed as a normal distribution with a mean of 700 and a standard deviation of 92.79. We are interested in the probability that Y is greater than 500. I have a normal distribution here, centered at 700. We're gonna put 2 standard deviations. That happens right at this point of inflection, right when this slope stops getting steeper and starts getting less steep. So this is about 792, and this is about 608. We want to know the probability that we get at least 500. That's an important word there, at least 500. So we want more than 500. So there's probably a good chance. That's pretty much 500 down there. And we want to know this area. Always draw a picture because it shows them that even if your math stuff is not great, you have a good concept of what's going on. This shows direction and the use of a normal curve. So let's calculate this probability. We could just go on our calculator and do a norm CDF with a lower bound of 500, an upper bound of a big number. Our mean is 700, standard deviation 92.79. We could type that into our calculator, but let's switch to Z's just to be safe. So we want to know the probability that the standard normal curve has a z-score bigger than the z-score for 500. So we take 500, subtract the mean, divide by the standard deviation. And if we then type this normal CDF into our calculator, we will get the probability 0.984, which checks out with our picture. So that is 2012. Thank you.